it's time, and let me just say one word before letting Masashi moderate this morning session. So there will be once again, as usual, two presentations today. One is the part two of Professor Hosono, but this afternoon, let me remind you that we go back to the usual time for the afternoon session, namely 4:30. Yesterday was 5 p.m. because the speaker was from the west coast of the United States, and so we had to give a little bit more time. But today we revert to the 4:30, and now I will let Professor Kawasaki moderate this session.
Okay, thank you, Mark. Welcome back to Professor Hosono's lecture. Today, I just input on the chat. You can input your question anytime during the lecture. Later on, I will name each of you, and you can ask questions to Hosono. And we have 75 minutes for lecture and plus 45 minutes for question and answers and discussion. So please input your question to the chat. Okay, so Professor Hosono, please make your presentation.
Okay, thank you, Kawasaki-san. Yeah, the last time, as I talked about electrolyte as material and the application to catalyst. And today's topic is ion-based superconductors. So please allow me to skip the oxide semiconductor, because the oxide semiconductor is now widely used to drive your iPad and so OLED TV. So that much more exciting as ion-based superconductors. Okay, and so this paper is a second paper on ion-based superconductor we reported. So this is a 2008 papers. Okay, this paper was published in maybe the March of 2008. Yes, yeah. This year, this paper was as most cited as among the all the discipline. Yeah, this citation number was world #1. Okay, so that yeah, here and I talk about ion-based superconductors. This is the outline, and so first is our research to the discovery, second is the parent material and the pairing mechanism. The third is it's more as detail, so the two-dome structure, NTC, and thin film fabrication, and first last is the application and summary. Okay, so as you know that it's formation of the Cooper pair is absolutely needed to induce a superconductivities. However, that as formation of the Cooper pair as completely compete with the magnetic ordering. Usually magnetic ordering is much stronger than the formation energy of the Cooper pair. That's why, and magnetic material cannot convert it into a superconductor. That was almost common sense in this community. This is a periodic table, and so iron, cobalt, nickel, each of them are well known as magnetic metals. So each metal have a ferromagnetism. Okay, iron is especially typical as magnetic material with large magnetic moment. That's why, and iron was very harmful to induce superconductivities. Okay, so I'll show that why we could discover the ion-based superconductors. And so our background research is P-type transparent oxide semiconductors. 1997, we reported a copper aluminum oxide as the first transparent p-type, it's oxide semiconductor, along with a design concept. So to improve the performance of the semiconductor, we moved to the chalcogenide. The base metal, the important metal is the copper 1+. Okay, this was very, very successful. The mobility is much enhanced and keeping a wide band gap. So our next target was to realize the magnetic semiconductor utilizing a strong DP interaction. As P interaction means that the hole is mobile at the top of the valence band, which is composed of the P orbital. That's why we need to dope the electrons. Okay, the copper 1+ is non-magnetic, so that we need to replace the copper 1+ ion with divalent transition metal cation. Okay, and so I check the database and it's the same crystal structure as the long-term copper chalcogenide, but position of the copper 1+ should be replaced by divalent first series and transition metal cations. Okay, so to keep electron neutrality, chalcogenide -2 should be replaced by nitrogen -3. Okay, so that we check the database, and we found that the large number of the compound lanthanum as transition metal nictine. The paper was reported by Professor Jaishiko of the German chemist. Okay, to my surprise, he reported that almost 200 or 300 compound and reported in 2000. Okay, but they just measure the crystals X-ray powder diffraction and reported as a lattice dimension. No properties, no physical property were reported. And I have a lot of experience in a phosphide material, so that we determine to choose the phosphide material and in this material in these families. Okay, so that the material we selected was lanthanum, oxygen, and transition metal 2+ and nitrogen 3-. Here is nitrogen is a phosphorus, arsenic, and antimonies. Okay, as a little bit experiment was difficult, but eventually we got a lot of experience to synthesize. Yeah. Okay, this is a result. Result we obtained. Okay, when the transition metal was changed from copper 1+ to manganese, iron, cobalt, nickel, and zinc. Okay, as electric and magnetic property totally changed with 3D electron numbers. So manganese case is a molten insulator. Okay, and molten insulator and magnetism is antiferro. Iron is a superconductor, and cobalt is a ferromagnetic metals. And nickel is again superconductor. Okay, and zinc case is of course semiconductors. It's a copper 2+ compound we could not synthesize till now. Okay, so that please watch this table. And when the electron count odd number, even number, as superconductivity come out. Okay, so the first we discovered the superconductivity was lanthanum, iron, oxygen, phosphide. Okay, this case is as a prepared sample shows the bulk superconductivity, but TC was 4K, not so high. Okay, but this is the first ion-based superconductor. And again, and in the 2007, we discovered nickel-based superconductors. And as the most important discovery is 2008. This time, and nickel is arsenic. And the oxygen, and a part of the oxygen is replaced by fluorine. This means that electron doping. Okay, so this layer is a conducting layer, and these two layers is of course an insulator. When oxygen is replaced by fluorine, electron is generated in this layer, but due to the offset, so the carrier electron should be injected this layer. Okay, so eventually, we found the superconductivities. Yeah, this is a low T curve of the parent material, so that looks strange. Okay, so around 150 K, suddenly its conductivity dropped and again come up. Okay, at first, positively, I'm very optimistic. Oh, this is a high temperature superconductor of TC equal 150. So volume fraction would be a very small. So that when as electron is doped, this volume fraction would be increased. But this is completely wrong. But when an electron is doped, bulk superconductivity come out. So these cases, and maximum TC is maybe 32. Iron-based iron is a magnetic metal, so that the pure ion doesn't show that the superconductivity, of course. But high pressure phase, this is phase diagram of the pure ion. When high pressure was applied, as ferromagnetism disappeared, crystal structure changed from BCC to HCP. So in a narrow region, it's very, very small. A low TC is appear, okay? Very high pressure. But in these cases, even ambient pressure as TC of the 30 K is induced. Okay, this is the first high TC iron-based superconductors. Essence was the electron doping. Okay, this is of course this is well known. This is the history of the superconductivities. So the superconductivity was discovered in 1911 in Mercury. After that, TC is gradually increased as the materials are intermetallic. Okay, but in 1986, so that cuplet superconductivity conductor was discovered by Bednout and Miller, and its TC is steeply going up. And it's pretty important is the discovery of the YBCO by Wu-San, Malcolm Wu, and Paul Chu. This material first exceeded a boiling point of the liquid nitrogen. Okay, and the maximum TC in high pressure is 130. Okay, and the 2008, Akimizu Sensei of Japan reported that as magnesium diboride. This is a BCC type, conventional superconductivity, BCS type. TC was 39. So that we discovered here the iron-based superconductor, and it's this is 32, and when high pressure was applied, TC goes up to the 43. After that, and it's a Chinese group replaced lanthanum iron with samarium. As a consequence, the TC goes up to 55 K. This is bulk record. Yeah, so the 2008 is very, very busy year. As the first international symposium on iron-based superconductor was held in Tokyo, and this next year, as APS March meeting, in the special session on the iron-based superconductor was held in Pittsburgh. Okay, so please focus in this person. Yeah, This is me, mine. So, so many people attended. Looks like a panda in zoo. Okay, so the 208 and the research was very urgent. Okay, this is a progress of the enzyme-based superconductors. So from 208 is February 26th. So only here until here, only our group did the research. After this paper was published online, and so many Chinese people joined a lot. This date, okay, please focus on that. This is a date, okay, not year. So that this data means that it's a date. A paper manuscript was posted on the convert. Very busy. Very busy. So that just replacing a lanthanum with other layers and some layers, so the TC is jumped to 55K. And other material was discovered by several groups, so that this is so-called 122 or 111, and most simplest is iron selenide is people call the 11. The simplest structure. After that, as various derivatives reported, and also the thin film publication was done. So our group is the first to publicate the epitaxial thin film, and maybe this one. I forget. Our epitaxial thin film, so that on August 11th. Okay, so that the iron was people believe that the iron was harmful to induce a superconductivity, but once the iron-based superconductivity was discovered, and after that, so many type of the parent compound have been reported to date. Now it's 10 plus 1 parent compound are already known. 10 means that it's a common structure unit. That is to say, it's a tetragonal lattice of the iron 2 plus iron. Okay, these 10 compounds are containing a common building block. Only one exception is a ladder type compound, and this compound doesn't show the superconductivity at ambient pressure, but under high pressure, this material, ladder type compound shows the superconductivities. But anyway, as important thing is the structure unit. Square lattice of the iron 2 plus is essential. So please compare the structure unit of the iron-based superconductor to the cuprate. So the cuprate cases, and cuprate at kappa distance is 4 angstrom. On the other hand, that iron-based superconductor, iron separation is 2.8, very short. Okay, this means, and also the nearest neighbor is, of course, this case, iron-based superconductor is nictogen or chalcogenide. But iron distance is still very short compared to kappa distance. This is a striking difference between iron-based superconductor and cuprate. Second neighbor of the iron 2 plus is very close. Okay, this is a recent progress of the iron-based superconductors. So the superstructure type. That superstructure type means that as a combination of the 10 parent material. Or this is one of the example. 1 to 2 plus the 1220. Okay, or the other is 122 plus 1 potassium 122 plus calcium 122. Such a combination and easily obtained so far. But the TC is still cannot exceed 55. But anyway, so many variety of the ion-based superconductor are already reported. Okay, so this is a structural classification of the parent material. Okay, a building block is classified like this, so that this is iron 2 plus square lattice, and this is a cation. This is the inside. Very, very simple. So variety is so many, but the prototype structure is very simple. Okay, so carrier doping is essential to induce bulk superconductivity and superconductivity. So the 1111 type, so the 1111, this is the 1111 type. We call the 1111 compound. So we discovered. Okay, so when before doping, the parent compound has its anti-ferromagnetic ordering, semi-metal. Okay, the structure transition, a superconducting phase is tetragonal. So that the room temperature phase is orthorhombic. So okay, but when the carrier is doped, as orthorhombic phase has become stable. Okay, and it's when the carrier is doped, so that TC is going down, and net temperature going down. After that, and the superconductivity come out. Anti-ferromagnetic phase is orthorhombic because of the spin ordering of this direction and this direction, both direction, perpendicular direction is completely opposite. That's why so dimension or lattice dimension is different. So the orthogonal, orthorhombic. The superconducting phase is tetragonal because of the anti-ferromagnetic ordering disappear as a consequence, and crystal symmetry change from the orthorhombic to the tetragonal. Okay, so there is no overlap between its magnetic phase and superconducting phase. This is a characteristic of 1111 phase. So the 1 to 2 phase, is a little bit different. So the parent material is anti-ferromagnetic, it's semi-metal. Lattice symmetry is orthorhombic. So this case is magnetic transition temperature and structure transition temperature is almost the same. And its electron is doped as the magnetic temperature is going down, and superconductivity come out. But the superconductivity, this region and anti-ferromagnetic ordering and superconducting phase coexist. This is totally different from the 1111 system. And so this region, so that extrapolated of the structure transition point is close at this point. This point is almost corresponding to the quantum critical point. So the presence of the quantum critical point in 1 to 2 is very clear. So such a quantum critical point is not observed in the 1111 system. Okay, so this is a Fermi surface topology. So that contrary to the cuplet superconductor, 5d orbital participate to the Fermi level. So cuplet case is only one d orbital. D is x square minus y square as participate to the Fermi level. It's very simple. But ion-based superconductor, all the 5d orbital participate to the Fermi level. Okay, and it's so iron, so except the iron, other element doesn't participate to the Fermi level. So that its main player should be it's iron. Okay, and this is the Fermi Fermi surface. You can see that the Fermi surface is a cylinder type. Cylinder type means that the electronic structure is a two-dimensional. This is 1111 type compound because of the 1111 type compound. The lanthanum oxy layer is sandwiched by sandwiched conductive layer. That's why the electronic structure of the iron nuclide cases is totally separated by an insulating layer. That's why the electronic structure and crystal structure are two-dimensional. 1 to 2 cases is the dispersion of the along the z-axis is also observed. So crystal structure is a two-dimensional, looks two-dimensional, but the electric structure is not pure two-dimensional for the 1 to 2 case. Okay, this is a Fermi surface. And as you can see that in the gamma point, and the gamma point is here, gamma point is here. This is a band. This is it's a whole band. It's M point is here. This is electron band. So this is a Fermi surface. So that it's two whole pocket is located in the gamma point. And the two electron pocket is located at the M point. Okay, that's why its shape and the curvature is almost the same. That's why parent material shows that it's nesting. Nesting is almost perfect. That's why parent material shows that the anti-ferromagnetic ordering. So when the carrier is docked, okay, gamma as pocket and its electron it's accumulated. That's why the area of the gamma point is continuously decreased. That's why so nesting is deviated from the perfect state. That's why anti-ferromagnetic ordering become weak and the superconductivity come out. So this is a model of the spin fluctuation. Okay, this is a phase diagram of the 1 to 2 system. 1 to 2 system is bipolar. Okay, so this is the electron is docked. So a part of the barium is replaced by potassium +1, so the hole is docked. Okay. The electron docked the case is here. So a part of the iron is replaced by cobalt. This is the electron docked. So the little bit strange. So my background is that it's a semiconductor. In the semiconductor, this is almost isovalent doping. Both have a two plus state, but so in alloy, so the copper, the cobalt 2 plus has one excess electron. That's why when the iron is replaced by cobalt, one electron is added. So that as a consequence, electron is doped. This is totally different from the semiconductors cases. But anyway, and both cases, and when the carrier is doped, superconducting dome come out. Okay, this is very simple. But on the other hand, another type of doping is possible. For example, please focus on here. This is barium 1 to 2 phases. A part of the arsenic is replaced by phosphorus. Okay, this is isovalent. But the TC when the phosphorus is doped, so that anti-ferromagnetic ordering is weak, weakened, and superconductivity come out. Okay, this is very rare. Such a cases in almost no in a cuprate or the other superconducting system. Ice valent doping is possible, pretty important. So almost the same thing happens in 1,1 case. Iron telluride or the iron selenide. Both are 2+, 2- are part of the tellurium is substituted by selenium, and so superconductivity come out. Electron constant count doesn't change, but local structure change. That's why superconductivity come out. This is totally different from the other systems. Okay, another important interesting property of the iron-based superconductor is the intercalation. Intercalation is well known in a layered compound. For example, this is a famous example of the hafnium and nitrogen chloride, reported by Professor Yamanaka. This is when this is a layered compound, and when in the interlayer, these various molecules are intercalated between layers. The TC is going up. Very, very strange. So obvious carrier doping doesn't occur, but child transfer, a partial transfer occurs. But anyway, as TC is much enhanced, but the maximum is located around here. Almost the same thing is observed in a 1,1 system. This is the data by iron selenide. So the parent material, iron selenide, TC is very low, 6K, reported by Malcolm Wu. It's okay, but when various molecules are intercalated between iron selenium layer. Okay, so some guy asks a question. So the strain as isovalent isovalent doping effect come from strain. Okay, so that is a reasonable question. In a sense, it's right. But strain is the permanent strain. Permanent strain means the chemical pressure. Structure modification occurs. Okay? Local structure, geometry is changed. Okay, it's a more detailed discussion. It's welcome after that. Okay, but parent material, the iron selenide is 6K, but when it's a molecule, this molecule is almost a nitrogen containing molecule. Such a molecule is intercalated. TC goes up to 46K. 46K, very huge, very huge. Okay, but always its maximum is below 40, below 50. Any kind of the intercalate cannot exceed the TC of the 50. Okay, and even the electrostatic doping by using electron double layer transistor structure, and so TC cannot exceed the 50. This is the current status. Okay. And after that, I will show how to exceed the TC equal 50. Okay, okay, this is a good timing. This is the relation between the TC and local structure. Local structure, especially this is bond angle around the iron. arsenic or chalcogenide, iron, and chalcogenide or the iron. Okay, that's 108.5 is the angle corresponding to the regular tetrahedron. Okay, this means that when the bond angle approach to this angle, so TC looks as highest, but so many deviations. But the general trend is light. Okay, because there are two factors to control the TC. One is the geometry. Okay, another is the carrier concentration. This data just shows that the local structure. Okay. So this, yeah, 5 minutes ago, some attendee asked the strain effect of the 1-1 system. Okay, so please focus on the 1-1 system. 1-1 system cases, it's okay, far from the optimum TC. Okay, bond angle is totally different and from the regular tetrahedron, but the TC is rather high. Okay, this case is and local structure model doesn't fit. Okay, and here so I will focus on the 1111 system because the 1111 system is have a highest TC, and also I'm sticking to our original material. Okay. So why TC is high of the 1111 system? This is a question. Okay, then another motivation is this is a schematic phase diagram of the 1111 system. When the electron is doped, net temperature going down, and instead the TC don't come out. Okay, but maximum doping level is 20% of electron. Okay, nobody knows that after 20%, why overdoped region is not realized. Very simple. Okay, so when the electron is doped, we replace a part of the OW minus ion with fluorine. Okay, and we discover the ion-based superconductor. But when the fluorine is much doped a lot, formation of the lanthanum oxyfluoride is preferentially precipitated. Lanthanum as layers oxyfluoride is very stable. So the solubility is determined by the precipitation of the layers oxyfluoride. So that we have to need 1 minus anion electron dope. What we selected for this purpose is H minus. Okay, H minus. I love H minus so much. Okay, this is the periodic table. So usually as hydrogen is located here. Okay, this is wrong in my sense. Okay, hydrogen is the simplest bipolar element. Bipolar means that the charge state is easily changed from plus to minus depending on the local environment. So the H minus, proton is very small, okay, almost it's 0 picometer. But H minus has a 2 electron, almost like a helium, so that the size of the H minus is pretty close to the OW minus or the fluorine. Okay, that's why we selected the H minus in place of the fluorine to dope electron. Okay, the problem is how to synthesize such a material. Okay, simple solid-state reaction between H- compound that so with the other ingredient. Of course, such a simple method doesn't work. So eventually, we selected this method. That is to say, and this is a target chemical composition. So oxygen is deficient. We prepare the batch so as to have such an oxygen as a deficient chemical composition. And as this ingredient put into these high pressure ambient cell, and as outer part is this material as a solid external hydrogen source was installed outside of the high pressure ambient cell. So that when the temperature goes up, okay, so that the chemical reaction occurs between sodium borohydride and calcium hydride. When the calcium hydride is heated, water molecule come out. Water molecule easily react with sodium borohydride, and hydrogen gas is involved under pressure. Okay, so that our assumption is the oxygen vacancy is less stable than H-. Okay, so that we can dope as hydrogen content. By just preparing this chemical non-stoichiometry, oxygen non-stoichiometry. So the X is, we expected that X is compensated by H- from the external hydrogen source. The pressure we applied is not so high, 2 to 3 gigapascal. Okay, and so we could obtain a sample, and we checked the chemical composition by using a spiral method. So that by EPMA and the hydrogen content is surely it's determined, and the hydrogen content is also determined by TDS, and as oxygen. Okay, so please focus on the summation of the oxygen and hydrogen. O plus H plus O is almost equal, almost 1. So this means that we don't need to consider the oxygen vacancy. And the next issue is the position of the doped hydrogen. Okay, we synthesize the Neutron substituted sample for the neutron measurement, neutron diffraction. So that the data is very, very simple. So that the model is oxygen site is partially substituted by the neutron. So the obtained pattern perfectly fit this model. So this means that the hydrogen substitutes the oxygen site certainly. Okay, so the problem is carrier concentrations. Okay, we measure the Hall effect. As you can see, the Hall effect, so that as we expected, when as hydrogen is doped, its electron concentration is continuous, goes up like this. Only this point is that this is a this region is a different region. This is anomalous Hall effect. But anyway, it's continuously going down. So this means that the electron concentration is continuously goes up. So the electron is surely doped into the sample. Okay, and this is the band structure, the calculation of the band structure. So that okay, so that the parent material is here. So the Fermi level is located here. Oxygen 2p is much deeper, and the fluorine cases, fluorine is much deeper, very, very deep. Okay, Fermi level is around here, but when hydrogen is doped, hydrogen level is also located here around its oxygen 2p level, so that's almost perfect. So it's a hydrogen and act as a H minus. Okay, and the integration of this partial dose almost gives almost 2, so that the 2 electron is attached to the hydrogen. This means that the hydrogen charge is minus 1. Okay, so that the problem, this is a phase diagram we reported in 2008. Okay, so that when the electron is doped, as net temperature going down and as superconductivity come out. So the almost this is close, but eventually, in fact, so we clarify that the whole bunches of the TC dome like this. Okay, is hydrogen doped sample trace fluorine doped sample data, and it's another superconducting dome come out. We call that as SC1 and SC2. Okay, SC2 is much wider than the SC1, and the optimum TC is higher than SC1. Okay, and temperature dependence of the normal state conductivity is different. So that in the SC1, the conductivity is followed to the T square. T square means that Fermi liquid line. So that but at the top of the SC2, so that the T linear. T linear is a non-Fermi liquid line. So that the cuprate superconductor is also at the T linear. Okay, so that now it is clear that in Lantram 1111 system, there are 2 TC dome. One is the old one, and below the SC2 is a newly found dome. Okay, so that we check the parent structure, the 2 dome structure by different beams, neutron diffraction, so that the x equal 0.5 is around here. So that around here, that this is parent phase is here, antiferromagnetic phase. So that we may expect that there are another phase around here, 0.5. Okay, so we examine the presence of the second parent phase by using various methods. The first is the neutron diffraction. You can see that as a magnetic peak appears like this. Okay, the intensity, okay, near temperature is around here. It's 9 to 80 K. So the near temperature of the TC2 is rather lower than that of the TC and parent 1. This is mu-SR. mu-SR is pretty sensitive to the local magnetic ordering. So that's okay. This is second within the second dome. When an electron is going up, and the electron is doped, so that the superconducting volume fraction is rapidly going down, so that the magnetic ordering phase should appear around here. So the synchrotron and the X-ray diffraction shows that another features. Okay, so the crystallographic transition is same from the orthorhombic to the tetragonal. But the parent phase around x equals 0 is a peak is split to the almost 1 to 1. But this case is split to the 2 to 1. Okay, this is a crystallographic phase is the same, but the space group is totally different. We analyze carefully the local structure. Okay, so the two are surprised. So that in a parent phase of the SC1, and so only only arsenic is replaced. Okay, but this case is another parent phases, and so arsenic and iron both are positive. So to the different direction. Okay, if there is no carrier, this material should be ferroelectric. Okay, so this is a kind of the Slater type insulators. Okay, this is a phase diagram clarified in heavily electron doping. So that there are two parent phase, and it's two TC domes, TC1 and TC2. So the parent phase is rather different. Both, of course, it's antiferromagnetic, but magnetic moment is rather different. Magnetic moment in its parent phase 1 is 0.6, and on the wire. So and in the second phase, the parent phase has its magnetic moment is 1.2, or rather different. It's the nature of the other electrical property between the two domes are rather different. Okay. Yeah. So the parent phase of the second parent phase is a little bit close to the iron tellurium, large magnetic moment, and its spin alignment. It looks similar. Okay, the SC1 as parent phase magnetic structure of the SC1 is close to 1 to 2 and 1 to 2. But the second 1 to 2 phase, the parent SC1 is close to 1 to 2, but the SC2 is close to the iron selenide, iron telluride. Rather different. So the most interesting system would be a Sm1111 1111 system, and with the highest TC. Okay, so that fluorine doped sample, its TC is observed up to here. Okay, that's 55K. So the hydrogen doped sample faithfully trace the data of the fluorine doped sample, but the TC dome is much extended, almost here, and going down. Okay, so that the TC dome has a top hat type shape and very wide. TC dome extended to almost 50% of electrons. But I'm very surprised. But unfortunately, TC is almost the same. Maximum is 55 or 56 kelvins. Doesn't change so much. But another issue we have to clarify that even this system is there. Whether another as the parent phase is located here or not. This is very important questions. Okay, but samarium system or the gadolinium system, and both there's element has a large, it's a huge neutron absorption coefficient. Okay, so the samarium and the gadolinium and the neutron absorber. So that neutron diffraction measurement is almost impossible by using it's natural abundant and layers. So we determined to prepare that isotope enriched 1111 system. This is very complicated synthesis method, but anyway, so we succeeded, and samarium 144 or 154 samples. Okay, this is the result. Okay, and yeah, parent phase and here is already known. that we found that another parent phase around here, a little bit complex, but don't mind. But anyway, it's this region, there is another antiferromagnetic phase around here. So that the two dome structure with two different antiferromagnetic phase is common for 1111 system. Okay, this is a summary of the magnetic structure of the parent phase, and AFM1 is almost the same. A magnetic moment is the same, and magnetic structure is the same. But AFM2 is a lot different. And the samarium system is a pretty large magnetic moment, and the spin configuration is different. Especially the interlayer as coupling is a lot different. Okay, so that please remember that the spin fluctuation model. So this means that yeah, parent phase has a two hole pocket and two electron pocket. And nesting is almost perfect. That's why antiferromagnetism is appear. Okay, when the electron dot, this nesting is a little bit weak, and as spin fluctuation induces superconductivity like this. Okay, but when as the electron is docked to 20%, whole pocket should appear, should disappear. Okay, this means that TC is going down, almost disappear. This is almost consistent with experimental data, but for the electron doping, TC is come out and increase a lot. This model doesn't work. What happens? This is another issues. Okay, so that we calculated as Fermi surface, and okay, so that this is SC1. SC1. This is as almost at the 20% doped sample. Okay, so that the nesting is yeah, whole pocket is weak, so that the nesting become weak, and also this is the totally weak. Okay, but the area of the whole pocket and shape of the electron pocket is continuously changed with doping level. Okay, so that for the band at d square minus y square, so that this and the whole band is continuously going down. It shrink, but pocket, electron pocket by this xy, the yz and zx doesn't change. Its degrees is not so clear, and also the shape is like this, from the hemisphere to trapezoidal. Okay, totally different. So that we measure the inelastic neutron scattering. So that inelastic neutron scattering directly is observed at the nesting vector. Okay, so that in SC1, this nesting vector just corresponding to the observed one. Okay, so we also detected the different nesting vector from the neutron inelastic scattering. So the nesting vector is a lot different. So that when we plot the nesting vector and in this as Fermi surface, so that just corresponding to here, another nesting occurs. Okay, so very surprise. Okay, so this data shows that when the electron is doped, main player of the D1 is switched in a low electron concentration region. These X, Y, Y, Z is dominant. That's in the spin fluctuation is dominant in this band. So after the minimum TC point, and the main player is changed from dxy, dxz, yz, and d square minus y squares. And it's eventually it's very strong and anti-ferromagnetic parent phase appears. So the build from here, so that the SC1 may be regarded as a hole dot. So the SC1 is regarded as an electron dot from the AFM1. Okay, very simple as the picture is obtained. Okay, this figure shows that the relation between TC and its energy gap determined by neutron inelastic neutron scattering. Okay, so that Q plate is here, and this is data of the SC1 and SC2. Both follow on a straight line, very clear evidence. And this is spin susceptibility as a function of the electron doping. When the electron is doped, spin fluctuation is going down, so and becomes zero. After that, it's jumped from here. Almost the same thing. Okay, so that we show that there is a two TC dome with different parent material. So this is the lanthanum 1111 cases. This is ambient pressure phase to dome structure SC1, SC2. When the high pressure was applied, what happens? Okay, this point, this is the minimum, but at this point going up and eventually is reach the maximum. So that the maximum TC is 52. So that only lanthanum 1111 system was believed to be as a low temperature as a superconductor. But you can see that this is TC exceeds 50K. Okay, this the result suggested us two parent phase. When SC1, SC2 merged into one dome, in such a case, maximum TC exceeds 50K. This is our conclusion. So we have to check another date. Okay, this is samarium 1111 system. Okay, so so high T to one dome structure is not specific to the lanthanum system. I will show the data. This is a samarium system. B is samarium and samarium system. Hydrogen doped. This means that electron concentration, doped concentration is controlled. So the arsenic is replaced by phosphorus partially. This means that the local structure is changed, so that we can independently control the carrier concentration and local structure by using this system. Okay, so as you can see that as one dome is obtained for the ambient and the non-doped, and this is y equals 0, and as y equals 0, so that TC is 55K. When phosphorus is doped, you can see that when the maximum TC is decreased, dome structure changed from the one dome to a double dome. Okay, when as TC is below 50, two dome structure come out. When as TC exceed 50K, one dome structure appears. So that So this is our conclusion. The one dome structure is needed to have a TC higher than 50. So the next question is, so why it's a large parent phase with large magnetic moment appears when an electron is doped? Almost looks like the insulator. Okay. We check the band structure by computation, so that the model is very, very simple. And when the electron is doped, as this is non-bonding state. This is anti-bonding state of the iron and it's arsenic. So that when the electron doped, this level and this level is switched. Okay, so this means the electron, added electron occupied at this level, but when the electron is doped, so that the non-bonding state have a half field state. So the half field state in a single band. So that this is almost like a motor insulator. But and so in an iron-based superconductor, and so several d orbital participate to the Fermi level, that only one orbital shows that motor insulating, so that the orbital selective motor state is realized. That's why it's localized nature. This means that high magnetic moment is induced in the parent space. Okay, so the theoretical model for the two-dome structure was reported by this is Croxon's computation, but I don't know that this is model based on the spin fluctuation, but the spin fluctuation, it's only spin fluctuation controls everything, but not so easy to believe, but not so clear. So the orbital spin and charge, which is dominant for the iron-based superconductor, maybe it's depending on the systems. Okay, the conclusion is very, very simple. And so to induce a high TC, higher than TC in the 50K, one dome structure is needed. Okay, one dome structure means that the two parent phase gives a different SC dome, and both dome merged give a higher TC. So the two parent phase they are needed to merge the high TC. This is our conclusions. So the remaining time is 6 minutes. Kawasaki-san.
Yes, you have something like 5–10 minutes.
Okay, so so the remaining time I will focus on the thin film. Okay, and the epitaxial thin film is important for its application. Yeah, so the is first deposit as epitaxial thin film was 122. 122 is very, very easy to fabricate the epitaxial thin film. Okay, so another is the important thing is fabrication of phosphorus doped as value 122. Because this system carrier is not doped, just chemical doping. So the structural change in this superconductivity, and the TC is high. And as I'll show that this thin film shows it's a very, very high JC. But that's high temperature deposition is absolutely needed. So that more than 1,000 degrees C is important, it's essential to have epitaxial thin film. So that's why we constructed such a system infrared laser diode system. And heat contact is also important. Okay, epitaxial thin film, and okay, but 6 minutes this is impossible to explain. Okay. The first slide shows that this is the recent data. So how to prepare the heavily hydrogen doped 1111 system. As this almost impossible to dope a hydrogen but heavy as hydrogen doped epitaxial thin film. So that we apply that post-annealing experiment, so that first the epitaxial thin film is created. After that, and it's heating with a calcium hydride powder in vacuated thin film, and eventually we obtained such a thin film. Okay, you can see that the hydrogen is substituted the oxygen position. So the oxygen, this sample, the hydrogen content is more than 40%, almost 50. So even the 50% of the hydrogen doped to the oxygen layer, no ordering is observed, but substitution is random. Okay, this is the TC data. So the maximum concentration, maximum TC is 448 Kelvin. So that is corresponding to the 35% of the hydrogen in the bulk sample. Okay, so that epitaxial thin film gives a pretty important information for applications. We fabricated the epitaxial thin film. This is a cobalt dope, 1 to 2 cases. It's tilted by crystal. So our subject, our target is to determine the critical tilting angle to keep a high JC. Okay, so that so we fabricated the epitaxial thin film, and so the substrate is I forget that this substrate isなんだっけあれシステムシステムってなんだっけこのバイクリスタルこのクリスタルバイクリスタル何使ったっけあれなんだっけな複雑なやつそうタンタルに入ってるやつエルサットそうそうエルサットYeah, the substrate we used was the LSAT. Okay, and so this is the data of the grain boundary dependence of the JC. Okay, this is data of the YBCO. Okay, you can see that the critical angle was 8 to 9 degree, which is more than double than the YBCO. Okay, and this is in the periodic formation of dislocation is observed. Okay, this period corresponding to the almost coherent length of the barium 122 system. Okay, this data encourages the people working for the Y application because the critical angle become double. So this is pretty good for the application. And also another important thing is the angular dependence of the JC. Okay, 1 to 2 is the crystal structure is two-dimensional, but the electric structure, crystal structure is two-dimensional, but the electric structure is pseudo three-dimensional. So okay, so that we check the as angular dependence. Angular dependence is not so large. As anisotropy is the maximum is 2. Okay, YBCO's case is one order higher, one order. This case is just 2, very small. And also JC, this is the JC data at 4K and 8K. So the very high JC is attended in even as high tilting arm. Okay, so that we fabricated as tape as coated superconductor on commercially available as metal wire. This data is pretty important. This is a substrate that's commercially available for as a cuprate superconductor, IBAD MGO tape. So you can see that, this data shows that JC doesn't change so much, but still as YBCO is much better. But as ion-based superconductor, keep a very high JC up to high magnetic field. This is a magnesium diboride. This is a commercially available as a metallic superconductor. So they're pretty robust to the strong magnetic field. This is pretty advantageous for the ion-based superconductor. So the most striking advancements was reported for the wire. So the ion-based superconductor wire is very easy to fabricate. Just the powder is input into the tube and is plugged in the mechanical plug. That's it. So the powder in tube method. Okay. So that after this paper, a whole group competed as a lot. NIMS as Chinese Academy of Science and the University of Florida. So that year by year, so that JC is going up. So that 2014, and JC reached the practical level. So that 3 or 4 years ago, so Professor Mao, the Chinese Academy of Science, fabricated more than 100 centimeter long tape. Okay, so even such a long tape, long wire, so that the homogeneity is pretty good. As JC exceed 1.2 times 10 to the fourth ampere per square centimeter. Now, as China is going to apply this material to the strong magnetic field application, especially as accelerator. Strong magnet for the accelerator is the first target I heard. Okay, this is the last view graph. Okay, this is a summary of the 3 representative and high TC and material: iron nictide, magnesium diboride, and the cuprate. So there's a critical difference between them is it's Fermi level. Only ion-based superconductor has a multiband. Multiband means that a variety of physics has come out, and also pretty robust to the magnetic field. Okay. This is another one. This is our paper. So that we so our team is concentrated on exploration of the new superconductor, and with these members, we found that 50 new superconductors, but most of experiment is not so successful. But we publish as unsuccessful list of the superconductor. Okay, so this means that please avoid the unsuccessful trial. With this data, this data would be helpful for the community. Thank you very much.
Thank you very much. Okay, so this lecture is open for question. So the audience, if you have question, please unmute and speak out. Is there any question?
Masashi, there is a question by Yorick.
Can I see it? Oh? Mark, you are talking about the question appearing in the chat?
Yes.
Yeah, this was already answered by Professor Hosono.
Okay.
Yeah. So then let me ask one question, Professor Hosono. You indicated a nice two-dome structure.
Yeah.
And also the pressure effect.
Yeah.
And when I saw this two-dome, in between you have a dip in TC, which is quite common observation for Q-plate if you have some stripe phase or some ordered phase. But in your explanation, in ion prectide, this is not the case. You don't have any ordered phase of this spinning of the orbital?
Yeah, the Q-plate case, I don't know that yes, people in the superconductivity area, they love the discussion a lot. That doesn't reach a final conclusion, even in the Q-plate superconductor. I don't know that which mechanism is acceptable for the Q-plate.
Yeah, but the fact is that if you observe very sharp dip in TC, people tend to observe some ordered phase. This is a common observation. So I thought in your case, you may have some ordered phase at 0.2 or something.
0.2 is no ordered phase, no ordered, because in the sharp minimum, and the minimum point located to the electron pocket disappear. A whole pocket disappear. So the nesting doesn't work, completely gone.
I see.
That's why it's a fluctuation. It doesn't work.
I see.
No order phase. The Q-plate case is charge ordering occurred around 1.8.
Yeah,
this is totally different. This is totally different.
I see. Is there any question from the audience? If you are shy, you can just type your question to the chat. I can read. Also says I can read. Okay. It's too clear. Mark, can we finish it if there is no question?
Yes, absolutely.
Okay. So let me make sure if any of you want to ask some question. Oh, we have one question. Thank you very much for. Could you have more comment on ion selenide?
Ion selenide?
Yeah, we got from Shijao Wang. He asked some comment on ion selenide.
Yeah. So the ion selenide case is a variety of the data. So that so especially the monolayer ion selenide is very, very complex. So that some group reported that TC higher than 100 SK, but nobody could be produced. Or and another substrate dependency is so strong. STO cases is pretty good, but other cases TC doesn't lace. I don't know the detail. But anyway, the most important thing is as carrier concentration is dominant. So that because the monolayer means that when the small carrier is induced, and so net carrier concentration becomes so huge. So that these data are consistent with as electron double layer as the result. When the carrier is docked, the TC is going up. So the but monolayer case effect is much more as clear, I think.
Okay. All right. Is there any more question? Okay. If not, let's thank the Professor Hosono for his lecture. Thank you very much.
Thank you very much. Okay.
Hey, Hosono sensei, thank you very much.
Oh, no, thank you, thank you.
Yeah. All right. So see you this afternoon for another lecture.
Okay.
So,
Thank
Mark,
you.
yeah.
Yes.
Can I finish or?
Yes, please.
Yeah.
Yeah.
Okay. Yeah. So see you